What's going on YouTube? This is the next video in the series on STM32F4 development, and in this video what we're going to be talking about is USART, Universal Synchronous Asynchronous Receiver Transmitter. It's essentially a serial protocol, so you can talk from one device to another. In our example here, what we're going to be doing is talking from or sending bytes from the ST board to our computer and back, and vice versa. We're going to actually implement the USART on two peripheral pins. So USART only uses two pins, transmit and receive. There's no clock lines or control lines in this compared to like I2C or SPI. It's strictly just transmit and receive. So we only need two lines for that. And then we're going to actually implement interrupt requests. So when we send data from the ST board to the computer, it's just going to be automatic right away. It's going to send out from the board to the computer. However, when it comes back, we don't want to sit there and poll like we did in the Blinky example with the button. We don't want to sit there and poll and wait for the user or the person on the computer to send us data back. It's just waste of CPU. So what we do is actually set up an interrupt request. So if the user on the computer sends data, then we'll start to receive at that point. The interrupt request will fire, and then we'll gather the data that way. All right. So let's get started. As you see over here on the left, or on the right on your screen, I have the ST board connected, two lines connected already. So one is transmit and one is receive. What I'm using, because I'm connecting from the ST board to my computer, to my laptop, I'm using a serial to USB converter. I'll try to show you here. This is the converter I'm using. It's just a USB to serial converter, and I have this connected to two lines on the board. I'm connected from the transmit line here on the converter to the receive line on the board that I'm going to be setting up, which is PA3. Then I have the receive line on this converter connected to the transmit line on the ST board, which is PA2. Okay, so just for wiring diagram, it's like that. All right, so now I'm going to take this converter and plug it into my computer. All right, and now let's get started with the code. So I already have a basic template project set up here, and a plain make file. So let's open this up and start editing. Okay, so here's our plain make file here. Okay, let's just minimize some of these things. So here's the systic. We can minimize the delay and minimize this, so it's all clean. All right, so as we know, the first thing we have to do is set up and configure the GPIO port. So the port PA2 and PA3. We have to set them up and use alternate functions, which is actually USART2. And again, I'm going to reference this a lot. Check out the ST reference manual, which is RM0090. Download it, definitely. It has all the information. This is where I'm getting that PA2 and PA3 or USART2, or have USART2 as an alternate function. And also you can check out this, the standard peripheral library manual. It's a similar thing, but the reference manual has more detail. Okay. So let's set up those two lines. So let's create a function here and just call it void setup GPIO, or setup peripherals, because in this case we're also going to be doing the NVIC, or the interrupt request. Okay, so we need, like in the Blinky example, we need to define first our initialization structures. So we need a GPIO underscore init type dev, and I'll call it GPIO underscore init structure. Okay, and now we also need to create a USART init type dev, and I'll call that USART underscore init structure. Okay, So now let's first, as always, enable the peripheral clock. For, in our case, USART2. So USART2, if you look at the reference manual, it's actually on APB1. So that's the clock that we need to initialize. In the previous example on like the Blinky, we were only worried about the GPIO port. Okay, so that's all that we had to set up. But in this case, we have to set up the USART2 and the GPIO port. Okay. So the pin that we're connecting to are both on GPIO-A. It's PA2 and PA3. So let's first enable this clock for the USART2. So it's RCC underscore. These are all functions from the standard peripheral library. APB1 peripheral clock command. And then we pass in RCC underscore AHB1 peripheral underscore USART2, since that's the actual peripheral that we're going to be setting up. And then we just want to enable. So we enable that clock. Now we need to enable the GPIO-A clock. So the GPIO-A clock is on, let's see, AHB1. Okay, so we can just copy and paste this, Control C, Control V. So it's on AHB1, so AHB1 peripheral clock command, RCC AHB1. Okay, sorry, up here I messed up. This should be APB1, and this one's AHB1 peripheral clock. And now we're setting up GPIO-A, enable. Okay, so now we have the clock for GPIO ports on GPIO-A, and then we have the clock set up for USART2. Okay, so both of those are done now. Now we have to set up the GPIO pins for transmit and receive. Okay, so this is where we use the GPIO init structure. So GPIO init structure dot GPIO pin. Now we set up the pins PA2 and PA3. So we can say GPIO underscore pin underscore 2, and then we can OR that with GPIO underscore pin 3. Okay, so we set up both pins 2 and 3. Now we can set up GPIO underscore init structure dot GPIO underscore mode. And now the mode that we need to set up in this case is an alternate function. For these two pins, USART2 is the alternate function. So we just need to set the mode first to alternate function. So we set this to GPIO underscore mode underscore AF for alternate function. Then we can set up init structure dot set up the speed underscore speed equals, we'll just set it to 50 megahertz. Speed underscore 50 megahertz. Okay, and now let's set up the output type, and we'll set it up as push-pull, same as the Blinky example. Init structure dot GPIO underscore output type, GPIO underscore O type underscore PP for push-pull. And now let's set up the pull-up resistors. So init structure dot GPIO underscore PUPD equals GPIO underscore PUPD underscore, and then we want a pull-up resistor on both of those pins. Okay, so now we can call the GPIO init function and initialize GPIO-A, and then pass it our GPIO init structure. Okay, so now PA2 and PA3 are set up for both they're set up for the USART2. We've set up the alternate function there. Okay, so now let's actually configure the alternate function. So let's go back to here, and so we've initialized PA2 and PA3, just the pins. And now what we can do is use another function called GPIO underscore pin alternate function configure. Since all we've done so far is say that it is going to be an alternate function, we have to actually assign an alternate function to that pin. So we assign to GPIO A GPIO underscore pin source, this is one word, pin source underscore 2, or actually pin source 2, GPIO underscore alternate function underscore USART2. Okay, so we set up GPIOA pin 2 as an alternate function USART2, and then we do the same thing for USART3. Okay, so now we've actually configured that the alternate function we're using is USART2. Okay, so now we actually have to define the USART2 configurations. Okay, so we can use the USART init structure. So USART init structure dot USART underscore baud rate. So the baud rate that we're going to use, which is pretty much universal, 9600 baud. Okay. Then we can figure out USART init structure dot USART the word length. Again, all of these that I'm using here are going to be pretty much standard for like a default. So the word length, I'm going to use 8 bits. So USART underscore word length underscore 8 B. So for 8 bits. So we have 9600 baud, 8 bits. We're going to do 1 stop bit and no parity bits. Okay. So we do USART init structure, USART stop bits equals USART underscore stop bits underscore 1. So 1 stop bit. I spelled this wrong. There we go. It's the only bad thing with using a text editor and not an IDE. It can mess up sometimes, just writing, and it takes a while. So we'll set up the parity now. USART underscore parity equals USART underscore parity no. So no parity bit. So we have 9600 baud, 8-bit word length, 1 stop bit, no parity bit. The next thing is going to be hardware control. Init structure dot USART underscore hardware. Here, let me just show you for reference where I'm pulling these from. So underneath the CHM, if you go to this is the USART init structure. So if we go to USART underneath the modules and we come down to USART, simply look at the data structures, and then we have an init type dev. Now here's the different members of this structure. So I'm just initializing all of these, the baud rate, hardware flow control, etc., etc. So we're setting up this USART init structure. And if you look at the basic initialization scheme, it tells you here what you need to set up everything. So you have to set up the baud rate, the word length, stop bit. This is under initialization and configuration. So that's what you do to set up the USART. Okay, so that's what we're doing now. So USART hardware flow control equals USART underscore hardware flow control none. So we don't want any hardware flow control. Then the next one is going to be the mode. So we want to set up both transmit, and we want to set up receive. So we set up these pins for both, or we want to set up USART2 for receive and transmit. we want to enable both of them. We don't want to just transmit data from the ST to the computer. We want to be able to receive it from the computer as well. So that's what that does. Okay, so now we have everything set up there, so we can call USART init, and you should see a pattern among all of these. So you always have init structure, and then you have an init to declare or to initialize the members. So we declare this USART init, call it with USART2, and pass the reference to our USART init structure. Alright, so now we have that USART set up. Now the next thing that we want to do is actually set up an interrupt request. Okay, the interrupt request is actually used so that when the user on the computer sends data to the board, we're not tying up the CPU polling, waiting for the user to send data back. So we're going to set up the interrupt request here. Okay, so the interrupt request actually requires us to modify or to use what's known as the NVIC, the Nested Vector Interrupt Controller. And it's exactly the same pattern as we've been using for GPIO and USART. So we have to declare, just like we did here, an NVIC underscore init type dev. NVIC underscore init structure. Okay. So now, again, if you go to the reference manual, you can see everything that you need to set up. The first thing that we should do is first say, okay, USART, we want to configure for an interrupt request, this USART. So we want to configure USART2, and then we want only USART interrupt request for receive. So we don't want the interrupt request for transmit. We only want the interrupt request for receive. Enable it. Okay. So we've enabled the interrupt request for USART2 on receive. Okay, so now we can modify the NVIC init structure dot NVIC underscore IRQ channel lowercase. So the channel is essentially the function name that we're going to be using, how we want to configure it. So we want to configure USART2 interrupts. So this is actually USART2 underscore IRQN. So we want to configure USART2 interrupt request. Okay. NVIC init structure. NVIC IRQ channel preemption priority equals 0. So this is highest priority here, or not the highest. You can go negative numbers; those are hardware specific. 0 sets it to the highest priority for a peripheral. The lower the number, the higher the priority. The higher the number, and this can go all the way up to 15. The lower the priority. So we want to set this to 0. So this sets the priority group of USART2. The next thing is to set the sub-priority group inside of the main group. So we have an NVIC init structure dot NVIC interrupt request channel sub-priority. Again, we'll set that to 0, so it's the top of its subgroup. Then the next thing, NVIC interrupt structure dot NVIC interrupt request channel CMD, which is essentially to enable the USART2 globally. So we can say enable. And now we can pass everything onto the init function. Okay. So then we just pass the address of NVIC init structure. Okay. So finally, all the properties are passed onto the NVIC init function, and now all that's left to do is simply enable the USART2 peripheral. So to enable it, we use the function USART underscore CMD, say USART2 enable. So that enables the USART2 peripheral. Okay, so that's all that we have to do to set up this peripheral. Okay, so now we can minimize that. So we have the peripheral set up. Now let's call it from main. So we set up sysdic, then we set up all the peripherals, which is the GPIO pins, the USART configurations, and then the interrupt request configurations here. Okay, so we can minimize that, minimize this. All right, so now we're back in main. What we actually want to do first, just to test this thing out, is to send data from, like, how do you send data from the ST board to the computer? You have to have some kind of printf function or something to output the data. So what we have to do is create a put string function that utilizes the USART peripheral. Okay, so there's actually a function called USART underscore send data. Okay, so that's how you send 1 byte, but how do you send 1 string? Okay, so we can create a function, and we'll just call it USART underscore puts, like put string, and then we pass in to this function a USART underscore type dev. Oops, not that one. USART underscore type dev. And it's a type def star USART X. So we can pass in any of the USARTs, USART 1, 2, 3, 4, etc. And then we also pass in, I'm going to make this a volatile char star S. So this is the string. We'll just say str. Okay. So we pass in what USART do we want to send this data out on, and what is the string. Okay. So now we can simply loop over the string. So while str is not null, we simply send the data, right? But the first thing that we have to do is check and wait for what's known as the TC flag, or transmission complete flag. So we wait for the transmission to fully be completed, for that flag to be set in the USART until we start sending data. Okay, so what we can do, there's 2 ways to do this. One way is simply say while USART, because it's USART2, you can just say USART X in this case, arrow the status register SR and this. So if you take a look at the reference manual again, let me see if I can get the page number. 1 second. Okay. In the reference manual RM0090, page 44, there's the USART register map. So if you look at USART underscore SR, it's the 6th bit is the TC bit. So we want to check, okay, is this bit set, or is it 1 or is it 0 essentially? If it's a 1, well, actually let's just write it out and we'll see. Okay, so we, in this case, USART X arrow SR. Now how do we get the 6th bit? We can simply AND this. Oops, we already have an AND there, with 0x040. 40 will be, yep, that's right. So that'll give us the 6th bit. And now what we want to say is, while this is not equal to 1, so while it's 0, or we'll just say, we'll just do that, stay here. So loop, so stay here essentially until this USART SR or the TC flag is 1. So it's, in this case it'll be 0. Transmission complete is not complete yet, so we'll stay here. Once the TC flag becomes a 1, then we break out of here and we can send the data. So we can say USART send data. And now the reason for, before I continue, the reason for this is you don't want to start sending data before, so like if we send out a T and an O, right? So we start sending out a T. If we don't have this here, the O will start being overwritten in those registers, in the output data registers. So we want to make sure that we completely output all of the bytes, all of the bits of T before we start the next byte. I hope that makes sense. Okay, so we finish sending 1 byte, then we can send the next byte. That's essentially what we're doing. So send on to you. So you send data, the data that we want to send it on USART X and send the value of str. So that's just the actual character. Okay, so this is one way to do this looping here. Another way to do that would be to say while, and this is using the functions, because in this case I had to figure out what's the 6th bit. In this case we can just say USART underscore get flag status, and then the flag status for USART2, and then what flag do we want to check? We want to check the USART flag, and this is a constant, TC. So we want to check the TC flag, and then we want to stay here while this is reset. Okay, so there's 2 different ways to do it. I'll just keep this way for now for clarity, and I'll leave this commented. But stay here while this flag is 0 essentially, or reset, and then send the next data. Okay, and then we also need to increment the value here. So increment this into your string. Boom. So this is our USART put string function. Okay, so this will send one string over USART to the other end, wherever it is. So from the ST board to the computer. All right, so that's done. So now what we can actually do in here, inside main, we can just say USART put string. Where do we want to send it? We can send it on USART2. And then what do we want to say? We can just say hello world, new line. And then we'll just while 1. So let's just run this real quick and make sure everything is working. I wrote a lot of code, so let's just test it out. So let me pull up the terminal. Okay. Pull it onto here. I'm not sure where I am. See desktop to, where's this? Examples. And then we want to go to USART. Alright, so here we are. So let's make this thing real quick. Everything's plugged in. You won't see anything on the board. Actually, I'm not sure if I'll even have that up on the screen. But what I am going to show you is I have this application called CoolTerm. Okay, so it's a COM port terminal thing. I already have it connected to my USB or UART to USB connector. I have it disconnected right now. We can just connect. So now it's connected. It's monitoring that USB. So anything that outputs from the ST board goes through that USB connector and then will show up here. So we should see hello world pop up on the screen once I press reset. So let's do make over here, compile everything. Hopefully there's no errors. Okay, and we do have a bunch of errors. Let's see here. Okay, so I fixed the errors. All it was I missed some semicolons right here. I wrote NIC, not NVIC here. What else was there? I had 2 USART.USARTs at this location, and then word length needs a capital L here and here. There was just some spelling mistakes. Okay, so now let's go back. At least I think it should be make. Okay, so now everything's good. Let's flash it. Okay, now let's pull up CoolTerm. Okay, here it is. So now when I press reset, here we go. There's hello world. Perfect. It's exactly what we thought. Now nothing is going to be transmitted back, but that's fine. So let's clear data. Let's disconnect for now. And now let's come back to here and finish up with this example. So everything's done on main.c, and we can actually just leave it like this, because what we're going to do is set up an interrupt request that will transmit the data back to the board, or that transmit data from anything that's received. Oops, sorry, that was my phone. That'll transmit any data from So we're going to set up the interrupt request to take any data that's received from the computer and send it back to the terminal. Okay, so we don't actually need to do anything else with main.c. We can simply just close out of that. But what we do want to open now is this interrupt folder or interrupt.c file here. Okay, so this is where all of the interrupts are going to go. So as you can see, when we open it, we have all these interrupts that aren't actually implemented. Here's sysdic handler that we re-implemented. So now what we can do is actually declare at the bottom of here our interrupt request handler. Okay, so we want to create void USART2 underscore IRQ handler. So this is USART2 interrupt request handler. It's passed in nothing. Okay. So let me just write a little comment. Interrupt request handler for all USART2 interrupts. That's fine. For all USART2 interrupts. That's good. Okay. So now the first thing to do inside of an interrupt is to check the flag, essentially, to check the interrupt request flag. So what we can do is the reason that you want to do that is because you want to make sure that this interrupt was the one that was intended. You want to make sure that USART2 was intended to be called. In case USART1 was intended to be called, you don't want to do the stuff for this. So let's actually let's check the flag. So if, and we can use the USART get flag status, but in this case it's going to be get IT status, so get interrupt status. It will return the flag to check if the flag was set. So USART2, and then we want to check the USART underscore interrupt RxNE. We want to check to see if that flag was set or not. If that flag is set, then we can handle all of our data. We can send the data back over serial. Okay, so now this means the data is the flag is set. So we can create just a temporary variable here which can hold a single byte. So every time this interrupt request handler actually gets called every time one byte is sent. So we can create a character variable, and we'll just say ch, and this equals USART2 arrow the data register. Okay, so when you set it equal to USART2 arrow data register, inside the data register is the byte that was transferred over serial to this interrupt request. So ch will be the byte that's sent over. So we simply access that byte. We got the byte. Okay, so now what we can do is actually check this character and then see, okay, is it the new line character? We can have some type of count so that there's a max number of characters that the user can enter. So let's actually do that. Let's implement a static integer count, or CNT, equals 0. Okay, so we'll have some max number of characters. We can say pound define max word length, and we'll just say 10. So the user can enter, I can enter in 10 things on the terminal on my computer before this interrupt request actually does something. Okay, so we have the character, we have the max string. Now we can check is that character, or if it's not equal to a new line, if it's not the new line character and CNT is less than max word length. So if the character that we read in is not the new line character, so the user hasn't pressed enter, and the count is still not exceeded the maximum word length, then what we can do is simply just store that character or output it directly. We could just output it right away. But what we want to do is, in this example here, store that word into some array or some string, and then output it once the user hits enter or they reach the word length. So let's actually create a volatile string here. Char, we'll just say received string, and then we'll set it equal to max word length plus 1. So we have that much room. So we have 11 or 10 characters that we can store in here. Okay, so we have this receive string. So now what we can do, they haven't reached the end of the string yet, so we can say receive string of the count equals ch. Okay, so store that character, and then increment. We can actually do it all right here. So receive string of count plus plus equals ch. So increment count and assign this variable here. Otherwise that means we've reached the end of the string, or we've reached too many words. So then we can say received string of ch equals \0, so end of string, reset count equals 0, and then we can send this string out over the put string function, USART underscore puts, and then we need to call USART2, and then we'll pass it receive string. Okay, the only thing left we need to do is actually tell this .c file where that USART puts function is. So extern void USART put string, and then it takes a USART. Actually, I can just copy from here. The put string function is here, so a USART type def and a string. There we go. Semicolon. There we go. So we have our interrupt request handler. So let me just walk through this one more time. So once this thing gets called, this interrupt request, every time one byte is sent from the computer to the ST board. It's every time the board receives a character. So first we check to make sure that this interrupt request is the one that was meant to be called. If it is, then we come inside. We have a simple counter to count the number of characters, and we have a character which stores the character that was received, which is stored in the data register of USART2. Then we check that character to see, is it the new line, or have we reached the max word length? If we haven't done either of those, then we store it into this string, receive string, and increment the counter. Otherwise, or once we've reached the end of string or the end of the word or the max word length, we assign the new line, the end of string character, reset the count, and then simply output it back to the terminal. So anything that I type into the terminal on my end on the computer, it will be sent to the SD board, and then right away it'll be sent right back to my computer. So I should be able to see it on the terminal screen. So if we save this, go into USART or go into the terminal, make this. Okay, there's one error here. Line 118, I said CH. This should be CNT. There we go. So now let's go back, make this. Okay, no more errors. Now what I want to do is pull up CoolTerm again. Let's connect. Okay, so we are not sending anything. Now let me double check in main. So we're sending so it should just say hello world once I hit reset. Well, let me flash this first. So we'll flash the board. Boom, it's okay, so now we're there. So now we're on the terminal. So once I hit reset, what's going to happen is we're going to see hello world, and then nothing's going to happen. So here we go. Reset. Hello world. Now we're simply waiting. Okay, we're not actually waiting. But once I start entering characters on my end on the computer, it's going to be sent to the ST board, and then once we've reached the max word length or I hit the enter key, it will be returned back. Okay, so now I'm going to enter in some characters on my board. So A, S, D, F. So nothing's happened on the terminal yet. I haven't reached 10 characters, and I haven't pressed enter. So now if I press enter, boom, it outputs directly back to the board or back to the terminal here. Okay, so we're sending data from our computer to the ST board. It's getting interpreted by the interrupt request. We haven't reached everything yet. Now once we press enter, it sends it right back to our terminal here. So now if I enter in 10 characters, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and then once I enter in one more, boom. So there's 10 characters there. It automatically sends it because that reached the end of the max word length. Okay, so now I can just hit enter, 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 enter. It still does the same thing. Hello world. It cuts it off because it's too many characters. So that's 10 characters there, and so on and so forth. So this is just one way. I hope this is fun for you. Whoops. So you get the point. So that was very simple, very quick. I tried to be as fast as possible. There's a lot of information here, so definitely check out the reference manual. If you have any questions, feel free to leave comments below. Again, please like and share and comment this video, and let me know things that you want to see or anything that you may be confused about. All right, until next time, see ya.